and introduce John Turner for the last case study that we're going to present today. John is a senior principal engineer with Dan Brown and Associates, and he's also Professor Emeritus of Civil Engineering at the University of Wyoming. He is the co-author of the Federal Highway Administration Drilled Shaft Manual, and also the author of the NCHRP Synthesis 360, which deals with rock-socketed shafts for highway structure foundations. And what he's going to present is yet another example of cost benefits of drilled shaft load testing. John, the floor is yours.
Thank you, Gerald. Yep, I'm here.
Now we do.
Okay, thanks. And thank you for those great presentations by Van and Matt. So I'm going to present examples of a couple more bridge projects with drilled shaft foundations where load testing was relied upon for support of both design and construction, and consider what the impact of load testing was, or in one case could have been, on the cost. So the first thing you see in this overview is a question. It says, how can we use load testing to achieve cost benefits? So in an attempt to answer that, we're going to look at two case histories. The first one is the Fore River Bridge in Massachusetts, and the second is the Antlers Bridge in California. So for each one, we'll look at how the load testing was integrated into the design and construction. We'll consider the impacts on the costs, and then we'll wrap it up by summarizing lessons learned in each case. So the first one is the Fore River Bridge. This is located south of Boston, spans a waterway between Quincy, Massachusetts on the north and Weymouth on the south. So the photo in the lower left is looking south towards Weymouth. You can see that it's a lift bridge, and the movable lift span is supported on two towers that we refer to as the Quincy Tower on the north and the Weymouth Tower on the south. So each tower is supported on two piers, and each of those piers is on a footing supported on 6 8-foot diameter drilled shafts with 7.5-foot diameter rock sockets. And the rock that's shown here, it's metamorphic argillite and slate of the Weymouth Formation, which is pretty prolific in the Boston area. And over the entire project, from all the borings, has a mean compressive strength of a little bit over 5,000 psi. So the soil overlying the rock is 100 to 125 feet deep. So to get down to those rock sockets, just in itself requires quite a bit of drilling. It's mostly alluvial, but there is a layer of dense glacial till right above the top of the rock, which, as we'll see, did pose some construction problems. So 2 load tests, both axial load tests, were performed, one at each of the 2 towers. So the objective of the load tests was to demonstrate the side and base resistances proposed for the design, but also to demonstrate that the proposed installation method was feasible. So they're demonstration and test shafts. And the method of installation involved reverse circulation drilling, which you see in the photo in the upper left shown here. So if you're not familiar with it, reverse circulation, it's also called the pile top unit. So the permanent casing is driven to the top of rock, and then the drilling unit, let me highlight that. Shown here, mounted on the top of the permanent casing. There's a drill stem, which you can't see because it's down in the hole at this point, but it has a full face rock rotary bit on it, and then it has a pipe, not right in the center, but offset from the center, which provides the reverse circulation. That is, the drilling fluid, which was water in this case, basically is forced up that tube. You've got water going down the hole inside the casing. and then that's being pumped down, and then the upward flow takes the cuttings out, and those are piped over to a disposal area. So it's a pretty efficient way to excavate a rock socket and basically provides something that's similar to an airlift for cleaning out the base. And that's the reason it was selected. And then you see one of the test shafts here, the concrete being placed by Tremy. So this table shows the original design parameters proposed for the drill shafts. And I'll just point out that the firm that provided this is a highly respected firm, knowledgeable, competent people, very experienced in the Boston area. And the design parameters, they are entirely consistent with what was in the AASHTO code at the time. I believe it was the 2012 version of the AASHTO LRFD bridge design code. So the rock properties from representative borings at each tower included the strength values that you see here, the 580 and 640 KSF, which I believe are in the range of about 4 to 4.5 KSI. Then using the rock mass rating, or RMR, which at that time was in the AASHTO code, you might be familiar with that. It's a way to characterize the rock mass strength based on things like the degree of fracturing as expressed by the RQD, the condition of the discontinuities, and some other factors, is combined with the compressive strength to obtain the predicted side and base resistances. So using those parameters, their original recommendations for the base resistance were in the 30 to 33 KSF range, and for side resistance in the 13 to 15 KSF range. And then if you sized up the shafts supporting those towers, using those design parameters, you would come up with socket lengths in the range of 30 to 50 feet. So at this point, we, Dan Brown and Associates, we were asked to take a second look at this and see if we thought we could obtain from this rock greater resistances in an attempt to reduce the socket lengths. And so the load tests were already proposed as part of the project. They were required by the Mass DOT. So this just shows a cross-section of the two load tests. So at the Quincy Tower, you can see it was a 5-foot diameter rock socket, 24.5 feet long. And you can also see that the rock over the length of this socket, not too good in terms of what you see in the RQD there. So first of all, we've got 8 feet of really weathered rock. The casing was installed and sealed into the top of that for a distance of 1.3 feet, as you can see there. And we don't get to anything really decent until this third core run down here with an RQD of 69. Then even below that, the next run, 23, short run with a decent RQD, and then again, another low RQD. So we weren't expecting a lot out of this socket, but we thought we could do better than the original design parameters. And then the representative boring at the Weymouth test shaft looks a little bit better. You can see we still have some weathered rock at the top. Then we have pretty decent recovery, very good recovery, and pretty decent RQD. And beneath the tip, we've got pretty good looking rock with an RQD of 82. So the results of the load test, which are summarized in this slide, well, unbelievable, really. I mean, you can see that in both tests, we maxed out the bidirectional load cell at about a little bit less than 14,000 kips, meaning each one of these was carrying a total of something close to 28,000 kips. And the mobilized side resistance in both cases exceeded 50 KSF. And the base resistance in the Quincy test shaft was approaching 300 KSF at just a couple tenths of an inch of displacement. And this one on the Weymouth side, where the previous slide showed the rock did look better, I mean, this thing really didn't budge at that maximum load. Only a tenth of an inch upward and only a couple hundredths of an inch downward. So that really did permit, for this project, the final drill shaft design was delayed until these load test results were available. So the results could be applied directly to the design. And in addition to just meeting the load demand, there were some other criteria for the socket lengths. Number one, all the sockets had to penetrate completely through the weathered rock zone at the top. There was a minimum length of at least 5 feet of embedment into the competent rock, and that was based on the boring logs. We had 3 to 4 borings at each one of the 4 pier footings, although most of them were not in the exact location of the drill shafts, but pretty close. And then the other third criteria there is that the minimum socket length would be one socket diameter of 7.5 feet. So utilizing the load test results there, this table just shows the range of socket length in the final design using the criteria that you saw in the previous slide there. And so instead of looking at 30 to 50 foot long sockets, we're looking at some were just the minimum 7.5 feet, and the maximum was 23 feet. So that eliminated approximately 650 linear feet of rock socket. And at the bid unit cost of about $1,500 per foot of rock socket, that gives a savings of almost $1 million, so $975,000. The 2 load tests, the total cost was $415,000. So the net savings in this case was over $500,000, $560,000. So that is an obvious benefit. Some of the key things to achieve that benefit were that the load tests were conducted well in advance of the final design, allowing the final design to take advantage of what we found in the load test. However, that's not the complete story here. So during construction at the Weymouth Pier, one of the 2 piers there were difficulties in trying to drill the socket through that glacial till that overlies the rock. Basically, the casing just would not penetrate that stuff. And then when the reverse circulation drill bit tried to go below the casing, it was caving in and trapping the drill tool down the hole, which was unacceptable. And they couldn't get down. They couldn't get it through to the top of the rock. So that did require, for 4 of the shafts at that pier, a complete revision to the installation method that I won't go through all the details shown here. That diagram is the submittal by the drill shaft contractor, who did an excellent job on revising their plan. But it was pretty involved, and it involved grouting ahead, then coring through the grout plug, putting a 7-foot diameter into the slot that was cut by the core barrel, then going back in with the reverse circulation drill, drilling through the plug to get down the rock, more casing and basically grouting in the casing, then drilling a smaller diameter, 6.5-foot diameter socket down into the good rock. So that did require that the design be revised. And if the original design parameters had been used, if we didn't have the load test results, those 6.5-foot diameter sockets would be on the order of like 60 feet long. But using those resistances that we got from the load test, those socket lengths were 20 feet. So that provided another cost advantage. So approximately $180,000 in addition to the $560,000, just because we had those load test results in our back pocket. And then the other thing here, and Matt did a great job there of putting numbers to the schedule, the time, and dollars to that time for the case there on I-35W. And I don't have that kind of data, but I can guarantee you that if these sockets had been the original length, of course there would be impacts to the schedule, but not just based on the original bid, but probably for additional difficulties in drilling into that rock. So we'll never know what those were because they were avoided in this case. And it was the load testing that provided that benefit to avoid making these rock sockets deeper than they needed to be. So just the upshot, the lessons from this Four River Bridge were, I think the benefits were the fact that we had the load test results and were able to apply them to the final design. And then the fact that we had the load test results when we did encounter construction difficulties, and then responding to the contractor's proposed revisions to the installation method, we were able to take advantage of those load test results. So the second case, this one is the Antlers Bridge. It's on I-5 north of Redding, California. It crosses Lake Shasta, which is formed by a dam on the Sacramento River. And the photos that you see here, basically the existing bridge that was there. And the reason it needed to be replaced was because it was seismically deficient. And you can see here that during the course of construction, the water level in Lake Shasta varied considerably. At points it was completely dry, like in the lower left. Then at other times it was almost up to the deck of the bridge. So this is a rendition of the bridge, which has been built and is in service. And you can see it's a 5-span bridge. So we've got 4 piers and the 2 abutments. The outer 2 piers you can see are supported on 2 columns, and the 2 inner piers are on 4 columns. Each one of those 12 columns is supported on a 12-foot diameter drill shaft, permanent casing again, down to rock, with an 11.5-foot diameter rock socket, which is a pretty good sized rock socket. And the rock in this case is the Bragdon Formation, which is a metasedimentary rock. You can see what some of the really good stuff look like in that core box in the lower right there. The mean compressive strength of this rock over all of the bridge piers there is in the range of like 8,000 psi, which is of course stronger than the concrete used in the drill shafts, which was had a design strength of 4,000 psi. And some of the rock lab compression tests gave compressive strengths as high as 30,000 psi. So this is rock which I would argue you don't want to drill more than you have to. And so drilling 11.5-foot diameter rock sockets in rock like this is pretty challenging, to say the least. And so the agency, in this case Caltrans, at that time in particular, and over the years, have had a philosophy about drill shaft construction in the wet and about counting on base resistance, whether it's in soil or rock. And so I was engaged in this project as a consultant to Caltrans, and I strongly recommended to them that they include base resistance, even though these shafts would have to be built in the wet, and that we run a load test in order to demonstrate that the contractor's means and methods would result in a rock socket that would mobilize base resistance at displacements that were compatible with those to mobilize the side resistance. So they agreed to that, although these load tests would not, the single load test, would not be performed really before the project was bid and contracted. So it would really be to just verify these assumptions at the beginning of the project. And they had their own estimates of what the side and base resistance would be, which resulted in socket lengths that were 40 to 60 feet. So we talked a lot about this ahead of time. You know, how could we utilize the load test results? Would it be possible to change any of the design once we knew this? And I guess there was very limited ability to do that. So just to show you again, these shafts were going to be installed using reverse circulation. So the production sockets, as we said, are 11.5 foot diameter. They felt like we needed to make the test shaft diameter at least half of the production shaft diameter. So these are 6.5 foot diameter sockets, 7 foot diameter casing down to rock with 6.5 foot diameter sockets. And so here's the reverse circulation drill that was used there. This is the pile top unit before it was inserted into the casing. You can see these weights are there to give some crowd or downward force on the cutting bit. There's a view of the cutting bit. You can't see the opening for the reverse circulation, but it's in there. And this shows the results of the bidirectional load test. And the first thing to jump out to you is just the magnitude of the load here. So again, the load cell was maxed out at 22,000 kips, meaning this socket was taking 44,000 kips of load, which is pretty unbelievable in and of itself. The upward displacement was on the order of 1/10 of an inch, and the downward displacement was a little bit over 1/2 an inch. So this gave unit resistances, which are shown in the next slide here, the table at the top, of 33 KSF side resistance at basically 1/10 of an inch of displacement, over 500 KSF of base resistance at 1/2 an inch of downward displacement. And you saw at the beginning, the rock strength is greater than the concrete strength. So this, my argument to Caltrans was you really do need to count on base resistance here. You're probably getting geotechnical base resistance that's greater than the structural resistance from the reinforced concrete shaft. And that turned out to be true. Based on the design strength of the concrete, you'd be limited to 420 KSF, which is pretty high. And we measured in the load test 532 KSF at pretty small displacement. I think that's a typo, the 0.14 inches. That was about 1/2 an inch of downward displacement. So what to do there? And just a photo of the reverse circulation drill that was used for the production shafts. So again, these had 12 foot diameter permanent casing seated into the top of that rock with 11.5 foot diameter sockets. So they did negotiate, even though the contract had been let, they basically decreased the length of the sockets by 10 feet in most cases. So instead of looking at 40 to 60 foot socket length, now they were revised to 30 to 50 foot long rock sockets in this pretty screaming hard rock. And then the cost savings, I think about $350,000 was split between the owner and the contractor. Now, if you actually use the resistances that were demonstrated in the load test, based on analysis, you could probably reduce those socket lengths to somewhere in the neighborhood of 15 to 20 feet, which would be like in the neighborhood of 2 to 2.5 socket diameters. And then what happened during construction, and I won't go into a lot of detail on this, but there were very significant claims on the part of the drill shaft contractor based on a differing site condition, claiming that the rock was way harder and also more abrasive than would be indicated in the boring logs. Even though the boring logs showed, lab test results of, like I said, rock up to approaching 30,000 psi. And then there were also problems down in the deeper portions of some of the rock sockets with caving of the rock, which really affected their production and affected the schedule. And they made claims based on that. So I'm not in a position to tell you what the numbers were on those claims, but I can tell you it was settled for a pretty large amount, millions of dollars. And based on their cost for drilling, these 30 to 50 foot long sockets in this, what they said was harder rock than indicated in the project documents, and also for the caving problems. So I think that the lesson learned in this case is that, yes, they took some advantage of the results of the load test by coming up with some decrease in the length of the rock sockets. But had they taken full advantage of those load test results, and maybe that would have required the load test to have been performed prior to the final design. But the time and cost, there would have been savings just on whatever the unit cost per foot of socket was. But really, the most significant savings would have come from the fact that the claims for caving would not have even happened because they were all more than 20 feet down into the rock. And then the claims related to the rock being harder than indicated would have been limited to much less length of rock socket than they actually were. So I think this was a case where they had a load test, and it did provide maybe some advantage, but not near what could have been taken advantage of. So I'll just conclude this by summarizing what I think were the important lessons here. And these two cases sort of contrast some of the, taking advantage of load tests and their impact on costs. And in the first one, there's I think it's obvious to everyone that if you perform load tests prior to the final design and you come up with resistances that allow you to reduce either the diameter or the length of the drill shaft, that there's going to be cost benefits there. And in most cases, and like what Matt illustrated there, it easily offsets the cost of performing the load test, and it has advantages to the schedule. But the not so obvious cost benefit is there when you have load test results and you have them to address problems that arise during construction. So the difficulties at the Weymouth tower there at Four River Bridge are a good example of that. We were able to accommodate the contractor's proposed revised installation method by redesigning those 6.5 foot diameter sockets in a reasonable and cost-effective way. And then, but on the other end of the spectrum, those load tests at Antlers Bridge, which were not taken full advantage of, was an opportunity to, I think, control costs a lot more than was done. So with that, I'll leave it at that for now, and I'm happy to take any questions, and I'll turn it back over to you, Gerald.
Thank you very much, John, for a very interesting presentation, and again, a very good indication that testing can be utilized and should be utilized, and it can avoid a lot of problems.